Right. Thank you. Good evening. I actually speak BGP, Verilog, and C far more often than I speak Go and Rust. And I do realize what I'm committing to getting into the meeting of the hardcore Go and Rust developers. And I already can sense the audience looking around for Rotten Tomatoes. However, at this time, I would like to discuss a little bit about what Go, Rust, and other components can do to the hardware, or what the hardware can do to them, and how to be friends. For a very simple reason. Vectorization, well, first, a step aside. Why this topic and why in 20 minutes? The lovely hosts of this meeting, they kind of suggested me that I try to squeeze 4 hours of a content into 20 minutes, as otherwise there will be consequences. So yes, I just did that. So vectorization works just fine. That's it. End of story. We can go to the pub now. However, not that fast. And turning back to a more serious topic. So vectorization has been with us for more than half a century, and in the x86 world for over 25 years. And the problem that we can see in the field is you have a really powerful hardware platform at your hands, but that does not necessarily mean that you're using it efficiently. And you might say that, why do we need to talk about this at all? Compiler is smart and can do everything for you. Yes, certainly it can do. Also, it can screw things for you very efficiently. On the other hand, if you want to squeeze the last % of performance from your platforms, you better be friends, be in a friendly terms with your underlying hardware. And historically, this has accumulated a large amount of, say, misconceptions, horror stories, and in general, facts which don't necessarily correspond to reality. There's a large cover of complexity or imagined complexity in all of these topics. So let's do a brief overview of what it is and how you can try to benefit from that potentially. So if we look from 2 angles, initially and historically, that was a domain of high-performance computations. So if you want to simulate some fancy physics device, you had to use those types of approaches. On the other hand, widespread availability of vector extensions on a commodity hardware, and yes, pretty much any of your laptop today based on x86, also architectures has that for free. You have already paid for that. The only thing that you need to use it explicitly in order to gain any benefit of it. So what's that vectorization? A really simple idea. If we look at the scalar algorithm or in a scalar processing world, we have one instruction and one set of data. If we extend that, and you might think that we are operating on arrays instead of scalars, we have one instruction which performs exactly the same operation on the multiple sets of independent data. This gives separate performance characteristics. You need to look into differences between the latency and the throughput, and that's not the same performance measure. From an x86 world perspective, that is called a SIMD, single instruction multiple data. That's just a marketing term for a fixed vector length. Some other platforms, both commercially shipping and experimental, have both fixed and variable vector lengths. We will discuss that a little bit later. And if we are talking about a practical and everyday, that means that you don't need to do that by hand. There needs to be a way where compiler is your friend and it does all the underlying dirty and complex work. Let's start from horror examples. And this is intentionally made a little bit on the horror side. SHA-2, so all you Bitcoin miners and security key storing experts, that's your domain. We have a simple and widespread cryptographical hash function. it does very trivial operations, shifts some bits left, right, rotates, does some exclusive ORing, some other trivial computations, and you get the result. If you look from the perspective of usability of processor resources, so we are running the same algorithm, and if we run the same algorithm on multiple instances of the data in parallel, technically that might be a benefit. On the other hand, as this is a widely used operation, processor vendors naturally start providing specific accelerated instructions for that. And certainly there are such ones for SHA-2. If we try to compare those approaches, and taking the scalar version as one, both for latency and throughput, accelerator certainly operates faster. And due to pipelining nature of all contemporary processors, it can have multiple instructions in flight, start the subsequent one while the previous one is not terminated yet, and therefore we have roughly 2.5 times increase in throughput. Now, if we look at the vectorized approach, there's not necessarily a full equivalence of scalar to vector operations. And in this particular example, we don't have rotate instructions implemented natively, and we need to do that ourselves. Therefore, the total latency of one pass through one SHA-2 block is less than compared to the scalar algorithm. But from the throughput side, we have a multiple times increase. And in this particular example, AVX512 gives you 15 times increase in total throughput. 15 times is not 15%. That's probably worth fighting for. Can you use magic? Well, a little bit before the details. This is the actual use case for that, coming from a networking world, the BGPsec signature validation. We have, well, multiple objects that need to be hash calculated and then verified or signed, and that easily can be done in parallel, provided that your data structures and layout doesn't conflict with that. And as a result, by trading in some latency, you get multiple times the performance. This is being used still not in fully production mode worldwide globally, but overall the world is moving in this direction. And it's a question of time when such type of solutions will be commoditized. So why do we need to care? Compiler is a smart one. We just need to select the appropriate command line switch, and it will do all the magic behind the scenes. Certainly, it will do for trivial cases, and certainly it will do for specific recognizable patterns, and that's mostly the processor vendor compilers, Intel and AMD, are fond of. If you look at the spec test suite results, and if you modify that just a little bit, you might see fascinating results of how the results change. However, for any other practical or say generic applicability of vectorization, the reality is very harsh. Compiler can help you, but it needs substantial guidance. You basically need to, well, mostly lead it by hand in order for it to provide you with any meaningful results. Otherwise, the end result will be, in best case, equivalent, but realistically worse than in the scalar way. So here's just a little bit of an example. You have a non-cryptographical hash function, this time for a hash map or hash table, Murmuro City, both 32-bit variants. And here the compiler starts crying that, sorry, I could not do that for reasons. So those reasons, if we try to generalize, they come into several larger groups. First thing, vectorization doesn't have control flow branching. There's no if. If just does not exist. You need to change control flow into data flow dependencies masking. and similar approaches. This is very dependent on the specifics of the underlying platform. Different generations and different families of specific platforms will behave differently, and you need to be aware of that. And if you really care about the performance, you end up building separate code paths for different families. This doesn't related to the fact that we don't have any form of control branching. This also depends on the data sequencing and interdependence between different element counts. If you are a hardcore cryptographer, you would be very happy with this. You get a free constant time algorithm. However, if you care about end performance, you better pre-sort your data before putting into the algorithm. Otherwise, you will have to, your latency will be equivalent to the longest of your data set and not to the average. So if we once again try to explain what the vectorization is in 20 minutes, 3 large groups. This requires what is called horizontal operations. Historically, vector processing was vertical. So you have multiple sets of data located horizontally, and you apply instructions vertically, and they just flow there from top to bottom. However, in order to successfully vectorize scalar algorithms, you need to have horizontal operations where data blocks or elements are rearranged within a vector. That is expensive from the hardware perspective. Expensive in the sense that, say, 25 years ago, when those things are being started to design, additional several, say, tens of thousands of transistors in a processor were too costly. Nowadays, spending several tens of millions of additional transistors for having an efficient shuffle unit for rearranging any to any on a byte level within a full cache line is just a rounding error in the total cost of the platform. Therefore, this is simply a natural hardware evolution path. The second big part is that you need to translate your algorithm from a control flow into the data flow. All sorts of branching, nonlinearities, looping, and other forms need to be serialized. Well, basically, you have one serial flow of instructions, and the differences in the control flow are mapped into masking or disabling or otherwise, say, multiplying by 0 or by 1 or adding 0 to your data. The third part, and the most important from a practical point of view, is that your data layout, your application structures need to be friendly to the hardware specifics. Alignment on certain boundaries, aligning fields within vector length, not crossing certain red lines, which are dependent on each specific and particular platform, and platform data sheet is your friend here. And overall, this means that in order to efficiently use vectorization, yes, you have the means, but first thing, you have to use those explicitly. And you have to help the compiler quite a lot in order to get any benefits out of that. Just standalone run through a highly optimizing compiler will not help. Because first thing, it is not necessarily aware of the platform specific. Second thing, it is not able to rearrange data structures in a way that is reasonably safe without understanding the logic of the overall program flow. And the third thing, yes, we do have certain experimental developments in a compiler community. If somebody is following that, that's multi-layer intermediate representation. Where you have the, say, traditional IR format being split into several different layers, one of them dealing more on the algorithm level and providing something like an intent for the lower level, intermediate representation from which structures closer to actual machine code are being generated. If we look briefly at the history of x86 vectorization, so that started with Pentium MMX back in the previous century, and while it was defined initially for what was called the multimedia at the time, video, audio compression, and things like that, the only remaining, impact out of that are so-called saturating instructions, where the operands don't wrap but stay at the minimum or the maximum value. That's history nowadays. Then streaming SIMD instructions, and the next step of advanced vector extensions, they introduced a set of new instructions and 128-bit lanes. And that is one of the red lines that we have, unfortunately, have to deal even today. So even if your, say, platform says that it supports 512 vectors, in reality, that's 4 times 128 due to the backwards instruction backwards encoding compatibility reasons. And if you look at kind of the pathway, initially it started as an integer only, moved into floating point, because at that time the marketing of processor vendors looked at the high performance computing market, and they had their own interesting requirements. Then it was realized that far more use cases are in the integer domain. This is how the AVX2 came in. There are some failures, some historical failures. The Larrabee, the Intel graphical processor, which they were trying to conquer the market at the time, brought in the foundations of what we have as AVX 512 today. The Xeon Phi, or integrated many core instructions, a rather specific and niche product, which was positioned again to the high performance computing, but with a rather universal instruction set. And eventually, with the Skylake family, we got the current contemporary AVX 512. So a few examples to illustrate, and we will skip quite quickly over those for the reasons of time. You might examine the slides in detail. So a trivial search for the pattern, right? So we have a structure, and 2 octets in that structure indicate a key, and we would like to count how many of those keys do we have. And we have different approaches of those. So rather naive, we have structures in memory, and we simply copy things in, mask some octets, match them, get the flags, multiply by what we add, and we get the result. And that gives us, well, 2.5 times increase compared to scalar. Not bad, really. So if we look a little bit smarter, we can actually not look into the full structure, but only to the keys. This saves twice the bandwidth of memory. If we go even smarter, we can only gather the elements which we are matching to. That once again gives us some benefit in throughput, but is costly from the latency perspective. We can do some unrolling, and this is probably the most optimal as it can get with this approach. Given that it's 8 times the performance increase, why not? Another often used operation, especially in a networking world, conversion between the big endian and little endian. And that's something that you're forced to do as all the, say, contemporary reasonable platforms are little endian, but the networking world is big endian. So suppose you have a structure which has different payload types and different interpretation of the payload types. And by the way, thank you, Go, for not supporting unions, really. Where you need to do big endian to little endian translation for different elements depending on the type. In a scalar way, that looks like that. However, a very efficient approach in the vector world might be simply to use the permutations. Now, as we have efficient permute units, and we paid all those tens of millions of transistors for that, so we craft translation vector, simply indicating which byte goes where depending on the indices, and you get roughly 3 times the performance boost. Why not? However, not everything is as nice as it might seem. We have that same trivial search example. However, this time our structure doesn't align to the platform. It's total of 9 bytes instead of 8. And what do we get here? We do cross the red lines. Well, first thing, 9 and 32, the common smallest divisor of that is 218, if I'm not mistaken. So you have to deal with quite a large block. However, for some of those elements, you cross the 128-bit boundary. And that means that the vector operations that you have defined, they are not applicable. You will have to mark those as exceptions. And very often, processing those exceptions will cost you more than doing even the basic scalar way. Well, with different optimizations and rolling and things like that, you can achieve something. But first thing, this is hardcore manual labor. Compiler will happily say, sorry, I couldn't auto-vectorize that because this doesn't look right. If we look at the other applications, the hash table or hash map, the overall approach is that you don't gain performance from vectorization in latency. You gain performance in throughput. Therefore, you need to process multiple elements at the same time. So instead of inserting or looking for separate elements in a hash map, you insert a block or search for a block of elements. And the end result, you get a vector saying that, okay, we have found those elements and here's the location, or we have inserted those and those were the duplicates. And the overall speed up is quite substantial. Again, provided that your hash function is vectorizable and maps to your underlying platform well. Multiplication here is a hard, expensive, and tricky operation. You can very easily overflow your vector lane, and you have to deal with extensions and eventually lose all the benefits. Now, trees, and trees are especially favorite flavor of data structure in networking. So again, a similar approach, you can insert or search for multiple elements in the same tree. However, if you look at the classical tree, that's a structure which requires branching. You compare the key and you go either this side or the other side. With vectorization, you don't have that at all. You need to map it into the data flow. That means that you calculate the left value, you calculate the right value, mask the one that is matching, and continue that for all the levels of the tree. Where's the problem? If one of your element requires 2 lookups and the other element requires 27 lookups, your total latency will be equivalent to 27 because you will have to wait until the longest of those searches is completed. Therefore, pre-sorting your data before dealing with the tree might give substantial results. Again, compiler itself is definitely out of steam to do those things, and you also need to do this more or less manually. So a few assorted random topics which have flown both in my experience over time, and I was dealing with the vectorization. So atomicity. You might imagine that in order to avoid all sorts of locking problems, you might acquire multiple locks at the same time with the help of vectorization. Well, you would wish, but unfortunately you cannot. Atomicity is not guaranteed at all. Even for fully cached aligned memory access, that is not guaranteed, and therefore you still need to resort to that same lock ordering. Memory ordering in general is implementation dependent, and if you have a split cache line, the results are unpredictable. They will be eventually correct. So the total store order of x86 is still holds, but it is not guaranteed which part will go first, which will go second. we do have a rather large fragmentation of vector extensions, and that is just increasing. Specific accelerators which are mapped onto the vector interface, like the matrix multiply units, certain extensions related to cryptography, and reusing the floating point multiplier hardware for the integer domain and things like that. An open question is interworking with the operating system. So if you have 32 registers of 64 bytes each, plus additional predicates and another flags, that's quite a large amount of context to be saved at each switch time. Operating system certainly can help you here if you help the OS. If you mark that registers or parts, say upper half or lower half of the registers are not used or are dirty. Otherwise, you end up paying quite noticeable cost for just for normal operation. Then, in order for the vector operations to work efficiently, you need to have data available and ready. That means speculative execution, speculative prefetching. However, the practical limitation of 4 kilobyte pages starts to be noticeable here. Speculation cannot cross the page boundary. And if your working set is larger than 4 kilobytes, you will eventually start losing the performance only because of that. And now some rather controversial topics which have been floating around in the industry and overall. So it's year 2022. Why are we talking about such low-level things like intrinsics and hardware interfaces and topics like that? Don't we have nice higher-level languages for that? We certainly do. Eventually, the compiler for those higher-level languages generates the code which runs on the underlying platform. How well it can generate the code and how well it can use the interface provided by the hardware and how hardware can expose that, it's a whole question of the overall performance. So some vocal software engineers at some point of time said that AVX 512 is obsolete and everyone should be punished for using that. Is that really true? Well, you should really reread what has been said and in what context. And overall, that is not true. It used to be true at some point of time. The technology and the limitations of those restrictions were mostly technology process based. And here you see a diagram of how the overall slowdown or frequency throttling works for different processor generations. And that's a question of time when that line will be mostly flat. It won't be fully flat. Laws of physics still hold. However, what used to be a sad fact of life 5 years ago, today that is no longer true. x86 is not the only platform in the world that is relevant. There are others, and there are upcoming platforms which have potential. They also have vector extensions. They are not compatible, and they will not be compatible, and there are no intentions for making them compatible at all. Just both not feasible and not practical to do that. So that means that we as an industry will have to live with that and simply maintain completely separate code branches if we care about the performance here. Portability. Reasonably bad and expected to get even worse, just for a simple reason that there is a feature set fragmentation. And that's related to normal market partitioning of the processor vendors. That is just a sad reality which we have to deal with. Compilers. Overall, compilers are getting slowly but getting better. It's probably a question of multitude of decades. I would probably be willing to say when we have mechanisms that might be said that they auto-vectorize reasonably well. Before that, there certainly will be tools that help, but well, we can say that it's a nice pipe dream that we write high-level code and that gets just magically auto-vectorized. And probably the question that results in biggest of the flame wars: what about the variable vector length? In academics, yes, they write tons of papers about that, and they really love this approach. If we look from a practicality point of view, from the industry, everyone hates that for the reasons that it's nice in theory, but once you try to feed that with sufficient amount of data from memory, you run into both memory bandwidth and memory management system limitations, and therefore that just does not work. It will probably continue as it is today in a scientific and very specialized, very high performance computing platforms. If we are looking into the generic compute platforms like x86 and potentially ARM, that is going to stay with fixed length for a foreseeable future, and that's good news. You don't need to build at least 2 different code paths for dealing with the full vector length and what is remaining. So that's a short story of a view into the vectorization from somebody who has to deal with both hardware and software interfaces. Who probably sees higher level languages somewhere there high above, which intend to do, well, nice things, but they don't necessarily succeed all the time. And with this, I would like to open. It's not only me spreading propaganda here, but probably a much more of a bi-directional discussion. So any questions, any comments, notes, gifts, or anything else remaining, I'm happy to listen.
Guess we have time for one question. Yeah.
I was just going to ask about SIMD and WASM.
Very contextualized question, right?
So I did hear something about that. I acknowledge that I didn't look into the details, but as we do have SIMD JSON, we have SIMD deflate or SIMDeflate or whatever the name for that is. I'm certainly not surprised by SIMD WASM, right? On a more serious note, you certainly can map multiple language constructs into the SIMD constructs, right? And that would be efficient. The question is how much your VM can look ahead and plan in order to fool the vector width. If you cannot do more, say, than 30% of the vector width, it's not worth doing. You will lose on the latency. If you can fill the full vector length and do, well, even a trivial addition operation, you will benefit from that. Pretty much the same story as for any other interpreted language, right? Take Lua, take something else. They have the same restrictions, and the performance is limited by how well the interpreter can look ahead and see what is coming after this current instruction, do certain level of speculation, and combine those into one execution unit. Any Rotten Tomatoes?
Thank you very much.